Hey everyone, it's Mr. Smith here, back for another video lesson. Today we're going to compare the distributions we've learned about. So the special types we've learned about are uniform, binomial, and hypergeometric. So we're going to do a short lesson today on just comparing them. A lot of the things I'm presenting to you, you'll have on the lesson sheet, so you don't have to copy a lot of stuff. And then we'll just do a couple examples where we identify which distribution will help us solve the problem. So let's get started. So I've given you guys a little organizer on your lesson sheet, comparing our three special types, uniform, binomial, and hypergeometric. And we'll just walk through them quickly. So with a uniform distribution, for an example of a uniform distribution, maybe a helpful one to think about as we walk through this. See if I can squeeze this in here. A single die, like 1 to 6, would be a good example of this, where n is really the only parameter we need to know in the problem. We need to know the number of items or the number of possible outcomes. So for a single die, that's 6. The definition of the random variable is the value of the outcome. So for the single dice, it's like either 1, 2, 3, 4, 5, or 6. So I think for this one, at least, it's pretty easy for me to write down those specific values. So you can choose to do that on your lesson sheet if you want to. The range of values for X, it depends on the situation. So for the single dice, the values are 1, 2, 3, 4, 5, and 6. But if you had, say in the game of life, there's a spinner and you can move like 1 to 10 spaces. Well, then you'd have, n would be 10 and your number of outcomes would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But a spinner doesn't just have to have numbers in order. Like you could have the numbers on a spinner be like a spinner. Let's say we have a very simple spinner with 4 equal sections. You get the numbers being 3, 5, move back 1, and 8. They don't have to be, it doesn't have to be in some kind of numerical order. So it depends on the situation. The probability formula is easy. So if you have 6 items, the probability formula, each item has a probability of 1 out of 6. So if you have n items, the probability is 1 out of n. The expected value formula for this just comes from the general formula we use for any old probability distribution. I'm just going to tuck that over to the side here. Remember that for any distribution, the expected value we get by adding up all the outcomes times their probabilities. Okay, and then since in this case the probability of each outcome is 1 over n, that just comes outside of the expected value formula because it's a constant. And you have the result here, 1 over n times the sum of all the outcomes. Of course, you could crank out the expected value the old-fashioned way, but this is a formula that can help make it quicker. And when you're doing problems, the big clue for when it's uniform distribution is if all the items are equally likely. And with this, we usually just do one trial. Like you roll a dice, you spin a spinner, something like that. A binomial distribution, we have 3 parameters. So the big identifying characteristic for a binomial distribution is that we're doing a bunch of trials and we're looking for how many times we had successful trials. N was how many trials we did. So we flip a coin 10 times, we roll a dice 8 times, et cetera, et cetera. In those examples of flipping a coin, rolling a dice, those trials are independent, meaning, if I flip a coin, the next time I flip a coin, the result of the first flip doesn't affect my second flip at all. So trials are independent. And trials also had to have the same probability of success and failure. We call those P and Q. And we do just note that those always add to 1 because it's success and failure. So always have to add to 1. Those are the only 2 possible outcomes. And our random variable X, our definition of that random variable was the number of successful outcomes. The range of values, well, if you're doing n trials, you could have 0 successes, 1 success, 2, all the way up to n successes. So there's a fixed amount of possible values that you could get. So for example, if we flipped a coin 4 times and wanted the number of heads, well, you could get 0 heads, 1, 2, 3, up to 4, and that's it. We developed this formula for the probability together in our video lesson. It involved combinations. This value kind of gave you the number of ways to arrange when your successes occur. We developed and talked about a nice shortcut for the expected value. It's just the number of trials times the probability of success. So it's really easy to use. You should use that. You could always use the general formula, but if it's a binomial distribution, make life easy, use the formula. And again, we use the binomial distribution when we have trials, it's success or failure, and the trials are independent, meaning P and Q don't change. When trials were, this should actually say trials are dependent. So I'll fix that on your lesson sheet for sure. So it should show up good for you there. Trials are dependent, meaning, that the probability of the next success changes from trial to trial. So an example of this would be like dealing out a deck of cards. And every time, say, you deal out a red card, the probability of getting a red card again changes because you've lost a card. And so to analyze hypergeometric situations, we use these parameters. We don't use P and Q because those will change, so we can't use that. We have N for the population size. So for I think for this one, it might work out for us to have, so I'll just put a deck, just for a deck of cards here. Population size would be 52. Let's say I was dealing out a 5-card hand. And I was counting, let's say, the number of face cards. So FC for face cards. Well, if you're dealing out a 5-card hand, that's 5 trials, 5 cards being dealt. And we're looking at each one of those trials and thinking of what is a success being a face card. And the number of face cards available is 12. There's 4 jacks, 4 queens, and 4 kings. The random variable is still the number of successful outcomes, but again, now the probabilities are changing. And the range of values, so if if we deal out 5 cards, the number of face cards we could get would be 0, 1, 2, 3, 4, or 5, the number of trials. So that's always the case. And we derived a formula for the probability of the number of successes in our video lesson on the hypergeometric distribution. It was this, and it won't go through it now because we've already done all that heavy lifting earlier. But I will say this would be a good resource to have, maybe when you're doing your any assessment or a big evaluation, and just have these with you, just to have the formulas. So I'm not expecting you guys to rederive all these formulas every time you're doing a problem. And we derived a formula for the expected value too in terms of R, A, and N. But of course, if you have the distribution and all the outcomes probabilities, you can use the old way, but it's definitely more practical to use that derived formula we had. When you're doing a problem and you are trying to think, okay, what type of distribution am I looking at here? I've got a little flow chart. This isn't like the be all and end all of choosing a distribution, but I found this helpful from the textbook I use. So in our current unit, we are just doing discrete random variables. We will talk about continuous random variables in a later unit. But for now, you guys are just focused on discrete random variables. So yes, it is discrete. If your problem involves trials with success or failure, so that would be answering yes to success failure trials, there's 2 options: binomial distribution, hypergeometric distribution. And the question to ask is, are the trials independent? Or is there a P, right? Is there is the probability of success for each trial the same, like flipping a coin or rolling a dice? Or is it different, like dealing out decks of a hand from a deck of cards? So, are the trials independent? You can think, well, if I was doing this as a binomial distribution, what would I use for P? If you can answer that question, then yeah, it's binomial. But if you can't, because the probabilities keep changing, then the trials are dependent and you would use hypergeometric. If it's not success and failure, if all the outcomes are equally likely, then you're at a uniform distribution. And if all the outcomes are not equally likely, then the answer is no. So an example of a distribution that was none of these would be, if you recall our game show analysis, the Wheel of Fortune wheel. If you want to even go back and look at that, we made a table of all the different probabilities for spinning different dollar values. And because some dollar values had more than one spot on the wheel, it wasn't a uniform distribution. So you can have distributions that aren't any of these three. We have looked at them actually. So any distribution where the probabilities are not equally likely could fall under that category. So have this flowchart handy. I think most of you guys, it'd be kind of automatic as to picking up when a uniform distribution would be. But is it binomial, hypergeometric? Just think, is there a P? So let's do a couple examples. This will go by pretty quick. We already have all the tools to do these. It's just now it's not necessarily saying, okay, we're in our binomial distribution lesson. Here's a binomial distribution example. Here you have to decide which distribution is appropriate to use. So if you'd like to, as usual, when we're doing these, pause the video and unpause when you're ready, you can do that. So our first question, we have a summer school class. We have 5 grade 11, 6 grade 12s, and 2 adult learners. And the teacher is making a group of 3 for a special project. We're interested in finding the probability that exactly 2 grade 12s are picked for the group. And then we'll find the expected number of grade 11s in the group, just as a follow-up. So first we have to decide, well, what distribution type am I looking at here? Going back to my flow chart, is this success or failure tries? Well, for part A, I'm looking for grade 12s. So yeah, it is. So a success would be a grade 12. Are my trials independent? Well, no, they're not, because every time I pick a student, the number of students goes down and my probability of getting a grade 12 student changes as well. So this is an example of a hypergeometric distribution. So now that we know that, we can identify our parameters. So the number of possible people being picked. We have 5 grade 11s, 6 grade 12s, 2 adult learners. So that'd be 13. R, the number of trials. So we're picking 3 people for a special project. So we're going to be picking a person 3 times, so 3 trials. And in part A, a success is considered getting a grade 12. The number of people in that success group, the number of available successes is 6. We have 6 grade 12s. And now we can solve part A. So we're looking for the probability that our random variable, the number of successes, is equal to 2. So again, if you want to pause the video, maybe check out our hypergeometric formula. Maybe try setting this up on your own first. You can do that, or you can follow along with me here. So on the bottom, number of possible groups of 3, 13 people, choosing 3 of them, and choose R. For the number of grade 12s, we have, so our successes, we have 6 grade 12s, A, choose 2, our number of successes, times, and then remember, for our failure combination calculation, all the left-hand numbers add up, all the right-hand numbers add up. So we have 7 non-grade 12s, and we're choosing one of them. 6 plus 7 is 13, 2 plus 1 is equal to 3. And we can evaluate this. I have not done this ahead of time, so I'll just do it along with you guys. I can probably do this by, no, I cannot. Definitely not do it I was thinking I could do it by just mental math, but then 13 choose 3 was going to be a pain in the butt. So no thanks. So the thing's exact for this one. 105 on top, 13 choose 3 on the bottom, 286. So that's exact. If you want to get that as a percentage, just divide, multiply by 100. Do that right now. So about 36.71%. You want to go to 2 decimal places there. All right, so you guys probably have lots of practice doing these kinds of questions, but we want to get comfortable identifying the type, picking off the parameters, then you can solve the problem. Let's do part B. So notice for part B, we're finding the expected number of grade 11s. So part B is changing up what a success is going to be. Now a success is a grade 11. So N is still 13. There's still 13 students. R is still 3. We're still picking a group of 3, but this time we'll use A equals 5 because we are now just talking about grade 11s. So A and B are kind of unrelated questions in a bit, right? They're different parameters. So keep that in mind. It's like a separate question, just kind of a separate scenario. The expected number of grade 11s, we'll use our expected value formula, RA over N, 3 times 5 divided by 13. So 15 over 13. So just over 1, grade 11. 15 divided by 13. About 1.15 grade 11s. And it's okay that we leave that as a decimal. We don't have to round to the nearest whole because this is an expected average, right? If this accounting class every day was making groups of 3 on average, there'd be about 1.15 grade 11s in that group. So there's our first example. So as we move into our second example, you could probably guess it's not going to be hypergeometric, but let's just make sure we walk through the questions on identifying. So I used to do this with my oldest, and this picture he's probably less than 1, but I'd put him in a laundry basket and just like spin him around. He never actually got sick, but that's where this question's based off of. So I'm spinning, let's say I spin Brian around in a laundry basket. And let's say in any given spin, there's a 5% chance that he'll get sick. So I'm in part A here, we're spinning him around 10 times. You know what, I'm actually just going to rephrase this problem. We're going to do get sick, let's say 2 times in 10 spins. So I have this actually changed on your, I have this changed on your lesson sheet. Just got to change it up here. 2 times in 10 spins. And how many spins can Mr. Smith expect to do before Bryden gets sick? So we're going to change that. How many spins can he expect Bryden to get sick? So those will be fixed up on your lesson sheet. So if we go back to our, definitely want to exit my PowerPoint. So if we go back to our flow chart, so we're spinning around Bryden. We have success failure tries. He gets sick. He doesn't get sick. And are the trials independent? Yes, in this case they are. I've said that each spin he's going to get sick 5% of the time. So it's possible for him to get sick like multiple times. Something to notice here is that we are considering Bryden getting sick a success, which we did talk about earlier, that it is possible for your success to be something you might consider negative. But this is a binomial distribution question. So if it is binomial, we got to talk about what's our P and what is our N and what's our Q. I don't like red there. Let's go back to navy blue. All right, so it is binomial. We are spinning him 10 times. So yeah, this will be fixed up on your lesson sheet there. We are spinning him 10 times. His probability of getting sick 0.05, 5% of the time, which means that Q is 0.95. Notice that's not given in the question, it's implied. If he's sick 5% of the time, he's not sick 95% of the time. And for part A, we are finding the probability of him getting sick exactly 2 times in 10 spins. All right, so here we go. So, he could be sick the first 2 times or the last 2 times or some combination in the middle. So there's 10 choose 2 ways to choose the 2 spins he gets sick. The chance of him getting sick twice would be 0.05 probability of getting sick to the power of 2. And then 0.95, he won't get sick 8 times. So we've set up our calculation. This problem might be pretty small. We'll see though. 10 choose 2. That should be 45, I think. Yep. Times 0.05 squared times 0.95 to the power of 8. So as a percentage to 2 decimal places, I got 7.46%. The probability that he's going to get sick exactly twice. For B, how many times can we expect him to get sick? So in this case, it's the binomial distribution, n times p. So 10 spins, 0.05, you get 0.5 times being sick. And again, we don't have to round that. That's kind of it's a predicted average. So 0.5 would mean so let's say, for example, because it's 5%, which is like 1 out of 20. Every 1 out of 20 spins, Bryden gets sick. So if I spun him 10 times and then another 10 times, that's 20 times. In those 20, I expect him to get sick 1 time. And so for those 10, that would divide by 2, and we get 0.5 times on average being sick. So sorry about the wording there. Definitely we'll fix that up on your lesson sheet. For next steps, I've got some practice for you guys. So a lot of these questions here have you rephrasing questions to change it from one type of distribution to another. So for a lot of these, answers may vary. So keep that in mind as you're doing those. Just to give you a heads up, I'm going to post a short assessment on the hypergeometric distribution. It'll be similar to what I gave you guys for the binomial distribution. Maybe I'll have you guys identify types of distributions too, but it won't be too heavy. Like your binomial distribution assessment was like create one distribution, solve a couple problems. It wasn't too bad. And my goal is to have review for this unit posted by the end of the week. And then next week, try to give you guys some time frame to when to get the Unit 3 assessment in. So at this point where we've been doing distance learning for about a month, and our unit tests are going to have to be, we'll have to be a little bit more flexible about when you guys can write them, because everybody's kind of working at a different pace, and and so we'll just have to chat about that. As usual, guys, if you have any questions, please let me know. Otherwise, I'll see you guys soon. Have a great day.